You are listening to Managing the Unseen, a clear guide to state in web applications. Like and subscribe to keep up to date on our latest audiobooks. Managing the Unseen, a clear guide to state in web applications. 1. Introduction. What is state and why does it matter? Imagine for a moment you're at your favorite coffee shop. You walk up to the counter and the barista smiles. You say, "I'd like a latte." The barista makes your latte. This is a simple, one-off transaction. In the world of web applications, we might call this a stateless interaction. The barista forgets you the moment you walk away, and the next customer starts a brand new interaction. But what if you approach the counter and say, "Hi, I have a loyalty card." The barista scans it, and suddenly they know your name, your usual order, and how many points you have. Then you say, "I want my usual, but with almond milk this time." They note the change. When you pick it up, they confirm, "Latte with almond milk for your name." When you return next week, they still have your loyalty points. This is a stateful interaction. The coffee shop, through its systems and the barista's memory, has kept track of pieces of information about you and your preferences, and these pieces of information influence subsequent interactions. In the world of web applications, this keeping track is what we call state. At its heart, state is simply the memory of an application. It's all the data that a web application needs to remember at any given moment to provide a specific experience or perform a particular function. Just like a person's working memory or a company's customer database, state allows an application to be dynamic, personalized, and interactive. Think about the websites and apps you use every day. Why do they feel so smart, so responsive, so tailored to you? It's because they're constantly managing their state. What kinds of things count as state in a web application? Your user input. Every character you type into a search bar, every item you add to a shopping cart, every option you select in a form before you click Submit, that's state. The application needs to remember what you've entered. Application settings. When you switch a website to dark mode, pick your preferred language, or adjust notification settings, the application remembers these choices. That's state. Data fetched from a server. The list of products on an e-commerce site, your social media feed, the weather forecast. All this information comes from a server and is temporarily stored and displayed by your web application. This data, while visible, is part of the application's current state. User interface, UI, conditions. Is a navigation menu open or closed? Is a pop-up dialog box visible? Is a button disabled because an action is in progress? These visual cues and interactive elements are also controlled by the application's internal state. Without state, every interaction with a web page would be like starting fresh. Imagine adding items to a shopping cart, navigating to a different page, and seeing your cart empty. Or filling out a lengthy form, only for all your input to vanish if you accidentally click outside the text box. This would be frustrating, to say the least. Why state management is crucial. The goal of modern web applications is to deliver a seamless, intuitive, and personal experience. Effective state management is the cornerstone of achieving this. Here's why it matters. Enhanced user experience. When an application remembers user actions, preferences, and data, it feels more responsive and coherent. Users don't have to re-enter information or lose progress. This fosters a sense of continuity and leads to a much more pleasant interaction. Smooth application flow. State guides users through multi-step processes, like a checkout flow or setting up a new profile. The application uses state to know where the user is in the process, what information is needed next, and what has already been completed. Data consistency. In a complex application, the same piece of data, like a user's ID or status, might be needed in many different places. Proper state management ensures that everyone is looking at the same, up-to-date information, preventing confusion and errors. Maintainability and scalability. As web applications grow larger and more complex, the amount of data they need to manage explodes. Without a clear, organized way to handle this memory, applications quickly become unpredictable, difficult to debug, and costly to change. This is often referred to as spaghetti code, where everything is tangled and changing one thing breaks another in unexpected ways. Thoughtful state management provides structure, making it easier for developers to add new features or fix bugs without introducing chaos. Consider the coffee shop analogy again. If the barista only remembered your current order and forgot your loyalty points, your past orders, and your name, the experience would be disjointed. Similarly, if the coffee shop's internal systems were a mess, with no clear way to track inventory, staff schedules, or customer orders, the whole business would grind to a halt. State management is the art and science of organizing, accessing, and updating this crucial memory in a consistent and efficient way. It's about ensuring that your web application always knows what's going on, what to do next, and how to react to user actions. Over the course of this book, we will demystify the concept of state in web applications. We'll start with the very basics, the primitive ways browsers store small pieces of information. Then, we'll explore how modern applications handle complex data within the browser itself. We'll confront the challenges that arise when state isn't managed effectively, and then dive into the powerful patterns and sophisticated tools that developers use to bring order to this often unseen but vital part of every interactive web experience. By the end, you'll have a clear understanding of why state is the beating heart of web applications and how to approach its management with confidence. 2. The building blocks. Primitive state in the browser. Before the sophisticated frameworks and global state management libraries we hear about today, web developers relied on straightforward, built-in capabilities of web browsers to store information. These fundamental mechanisms, though often simple and limited compared to modern solutions, are the foundational building blocks of state management. Understanding them provides crucial context for appreciating why more advanced techniques became necessary. Imagine the web browser as a small, specialized office. This office needs little notepads and filing cabinets to remember things while you're browsing the internet. These built-in storage mechanisms are those notepads and cabinets. Browser storage, why the browser needs memory. When you visit a website, data often needs to be stored on your computer by the browser. This could be to save your login session, remember a temporary preference, or even cache parts of the website to make it load faster next time. This local storage allows web applications to offer a more personalized and efficient experience without having to constantly ask the server for the same information repeatedly. Let's explore the primary ways web browsers assist in managing state. Cookies, the old faithful and its quirks. What they are. Cookies are perhaps the oldest and most widely recognized form of client-side storage. They are small text files that a website sends to your browser, which your browser then stores. When you revisit that same website, your browser sends the cookie back to the server. Use cases. Session management, the most common use. When you log into a website, a cookie often stores a unique identifier, allowing the website to remember that you're logged in as you navigate between pages. Without this, you'd have to log in on every single page. User preferences. Remembering simple settings like your preferred language, region, or a user-selected theme. Tracking. Less about application state and more about user behavior. Cookies are also widely used by advertisers and analytics services to track your browsing habits across different sites. This is where cookie consent banners come from. Characteristics. Sent with every HTTP request. This is a key distinguishing feature. Every time your browser asks the server for a page, an image, or any other resource from that same domain, it automatically sends relevant cookies back to the server. Limited size. Cookies are very small, typically restricted to about 4 kilobytes (KB) per domain. This is not much data at all. Expiration dates. Cookies can be set to expire after a certain amount of time or when the browser session ends. Domain restrictions. A cookie set by example.com cannot be read by another -site.com. This is a security feature. Limitations and concerns. Security. Because they are sent with every request, cookies can be vulnerable to certain types of attacks if not handled carefully. For instance, if an attacker could trick your browser into sending your login cookie to their malicious site, they could impersonate you. This is a complex topic often discussed under terms like cross-site request forgery, CSRF, and cross-site scripting, XSS. Privacy. Due to their use in tracking, cookies have raised significant privacy concerns among users and regulators, leading to cookie consent pop-ups being common. Analogy, think of cookies like little ID badges or luggage tags. When you enter a specific building, website, you're given a badge. Every time you move through a door within that building, you show your badge. The badge has limited space, 4 KB for information, and might expire today only. If you go to a different building, you get a different badge or no badge at all. Web storage. Local storage and session storage. The limitations of cookies, particularly their small size and the fact they're sent with every request, which can waste bandwidth for large amounts of data, led to the development of web storage. This set of modern browser APIs provides more spacious and flexible ways to store data directly in your browser. Local storage, the persistent notepad. What it is: local storage allows web applications to store data as key-value pairs without an expiration date. This data remains in the browser even after the browser window is closed, the computer is shut down, or the user navigates away from the site. It's like a permanent sticky note for that website. Use cases: user preferences, saving user-selected themes, e.g., dark mode, layout choices, or initial startup settings. Client-side caching, storing data retrieved from a server that doesn't change frequently, reducing the need to fetch it again on subsequent visits. Offline capabilities, storing data for applications that need to work partially or fully offline. Characteristics: larger capacity, typically 5 to 10 megabytes (MB) per origin website, a significant upgrade from cookies. No automatic transmission. Data stored in local storage is not sent with every HTTP request. You have to explicitly read it using JavaScript. This makes it more efficient for larger data sets. Persistence: data remains until explicitly cleared by the user or the application. Analogy: local storage is like a personal library card or membership card you keep in your wallet. It stores your preferences for that specific library, and it's always there when you return, even if weeks pass between your visits. Session storage, the temporary scrapbook. What it is: session storage is very similar to local storage, but with one critical difference. Data stored in session storage only persists for the duration of a single browser session. This means the data is available for as long as the user has that specific browser tab or window open. If they close the tab or window, the data is gone forever. If they open a new tab to the same website, it starts a fresh session storage. Use cases: multi-step forms, storing user input as they progress through a multi-page form, ensuring that if they accidentally navigate away or refresh, their progress isn't lost within that session. Temporary user data. Any data that needs to be retained only for the current browsing session, like temporary filters for a search result or the state of a wizard. Characteristics: larger capacity, similar to local storage, typically 5 to 10 MB per origin. Session-specific, cleared when the browser tab window is closed, not shared across multiple tabs of the same origin. Not transmitted. Like local storage, data is not sent with HTTP requests. Analogy: session storage is like a temporary sticky note you put on a book you're currently reading at the library. It helps you remember your place and specific pages while you are actively reading that book in that session. Once you return the book, close the tab, the sticky note is removed. URL parameters, simple, visible transfers. What they are: URL parameters are pieces of data appended to a web address, visible directly in the browser's address bar. They appear after a question mark and consist of key-value pairs connected by ampersands and, for example, www.example.com/search query equals books ampersand page equals 2. Here, query and page are the keys, and books and 2 are their respective values. Use cases: filtering and sorting, passing search terms, filter options, or sorting preferences to display specific data. Deep linking, allowing users to share links that immediately navigate to specific content or a pre-filled state. Simple state transfer, occasionally used to pass very simple state between pages or to initialize an application with certain values. Characteristics: visible and shareable. Because they are part of the URL, they are easy to see, bookmark, and share with others. Limited size. URLs have practical length limits, typically a few thousand characters, making them unsuitable for large amounts of data. Public visibility. Any sensitive information should never be passed via URL parameters, as they are easily intercepted and stored in browser history. Analogy. URL parameters are like writing a specific street address and apartment number for an apartment building. Everyone can see the address, and if you send it to someone, they can go directly to that specific location. Choosing the right tool. Each of these primitive storage methods has its strengths and weaknesses. Cookies. Best for small pieces of data related to maintaining sessions, e.g., login status, or very small, non-critical preferences. Local storage. Ideal for larger, less sensitive data that needs to persist across browser sessions, such as user themes, cached static data, or offline assets. Session storage. Perfect for temporary data that should last only for the current browser tab's lifetime, such as progress in a multi-step form or a temporary shopping cart. URL parameters. Useful for simple, public, and shareable data that directly influences the content or view of a page, especially for initial filtering or navigation. These browser-native state mechanisms form the foundation of how web applications can remember things. While they are useful for specific scenarios, they are often insufficient for the complex, dynamic state requirements of modern web applications, especially those that behave more like desktop applications than simple websites. In the next chapter, we'll delve into how applications manage their internal memory beyond these basic storage capabilities. 3. Client-side state, from simple forms to complex interfaces. In the early days of the web, most websites were simple documents. You'd click a link, the browser would request a new page from the server, and the server would send back a whole new page. Each click was a fresh interaction. These were largely multi-page applications, where the server was responsible for creating most of the user interface and managing most of the state. However, the web has evolved dramatically. Today, many of the websites we interact with feel more like desktop applications or software living directly in our browser. Think about your email client, a mapping application, or a collaborative document editor. You rarely see the browser refresh the entire page. These are known as single-page applications, SPAs. In SPA, much of the user interface is built and updated dynamically within the browser using JavaScript, rather than constantly fetching new pages from the server. This shift towards SPAs means that a much larger portion of the application's memory, or state, now lives directly in your web browser, on the client side. In memory state, the application's short-term memory. Beyond the persistent storage mechanisms like cookies and local storage we discussed in the previous chapter. Web applications also need to hold data fleetingly in their active memory. This in-memory state is like an application's working RAM. It's what keeps track of everything happening while the user is actively engaging with the application. Basic variable storage. At its simplest, in-memory state is just data stored in JavaScript variables. For example, if you have a simple calculator web page, the numbers you've entered and the operation selected, plus, asterisk, are stored in variables in the browser's memory. The ephemeral nature. A crucial characteristic of in-memory state is its impermanence. When you close the browser tab, refresh the page, or navigate away, this state evaporates. It's designed for the immediate interaction, not for long-term storage. User interface, UI state, how components remember themselves. Modern web interfaces are often built from smaller, reusable parts called components. A component might be a button, a navigation bar, a shopping cart item, or a whole section of a page. Many components need to keep track of their own internal memory to function. This is often called component-level state. Imagine a restaurant, a closed for cleaning sign. This sign needs to remember if it's currently open or closed. When cleaning begins, its state changes and it displays closed. When cleaning finishes, its state changes again and it displays open. Its state is solely its own concern. A table's status light. Each table might have a small light that indicates if it's available or occupied. When customers sit down, the light changes to occupied. When they leave, it changes back to available. This light manages its own status independently of other tables. In a web application, component-level state works similarly. A like button, it needs to remember if it has been liked or unliked by the current user. When clicked, its state flips and its appearance, e.g., color, text, updates to reflect this change. A drop-down menu. It needs to know if it's currently open or closed to show or hide its options. An image carousel. It needs to remember which image is currently displayed. When you click the next arrow, its internal state updates to the next image in the sequence. The challenge begins when these individual components need to communicate or share information. What if clicking the like button also needs to update a likes counter component elsewhere on the page? How do these two separate table status lights signal the host that no tables are left? This is where the limitations of strictly localized component state start to emerge, leading to more complex state management patterns. Form state, the unsubmitted truth. Forms are a classic example of client-side state in action. As you type into an input field, select an option from a drop-down, or check a checkbox, the application is constantly updating its internal memory of that form's data. Consider a multi-step registration form. As you fill out personal details on step 1, the form components hold your name, email, and password in their in-memory state. When you click Next, this collected data becomes part of the application's broader in-memory state, allowing step 2, address information, to build upon it. If you encounter a validation error, the application uses state to display error messages next to the problematic fields, even before submitting the entire form to a server. This temporary storage of form data on the client side allows for immediate feedback through validation, a smoother user experience as you navigate complex forms, and the ability to save progress locally before final submission. The concept of reactivity. Modern spas often leverage a fundamental principle called reactivity. In simple terms, reactivity means that when a piece of data changes, anything that depends on that data automatically updates itself. Think back to the restaurant. When the host changes the table 5 status from occupied to available, the light on the table automatically flips back to green. More importantly, the central screen that the waitstaff uses to see available tables also instantly updates to show table 5 available, without someone manually going to the screen and changing it. In web applications, if a component is showing a user's name, and that name is updated in the application's state, perhaps after the user changes their profile, any part of the UI displaying the old name should react to this change and automatically display the new name. This automatic update creates a highly responsive and dynamic user experience, eliminating the need for developers to manually tell every part of the UI to refresh. The need for structure. As applications grow, the sheer volume of in-memory client-side state can become overwhelming. Multiple components might need to share the same data, or a change in one part of the application could unintentionally affect another distant part. Imagine trying to manage a restaurant where every waiter, cook, and host keeps their own separate mental notes about customer orders, table statuses, and inventory. Chaos would ensue. The challenge then becomes, how do we manage this ever-present, ever-changing client-side memory in a way that is predictable, maintainable, and prevents bugs? How do we scale from simple forms to complex, interactive interfaces without developers getting lost in a labyrinth of interconnected data? This question is at the heart of state management challenges, and it's what the subsequent chapters will address. We'll explore how developers bring order to this intricate network of in-memory data. 4. Server-side state. The backbone of data persistence. While client-side state is crucial for providing dynamic and responsive user experiences, it has a fundamental limitation. Most client-side state is temporary. If you close your browser, switch devices, or if the data needs to be securely accessed by many people simultaneously, the ephemeral nature of client-side memory becomes a problem. This is where server-side state comes into play. Server-side state refers to any data that is stored, managed, and processed on a server. It is the persistent brain of many web applications, ensuring that information is available reliably, securely, and consistently across multiple users and over long periods of time. Everything from your social media profile to your bank balance, from the products in an online store to the articles in a news feed, is managed as server-side state. Let's explore the key components that constitute server-side state. Databases, the grand filing cabinet. The primary mechanism for storing server-side state persistently is the database. Imagine a database as an incredibly organized, secure, and vast digital filing cabinet, designed specifically for storing, retrieving, updating, and deleting information. When you create an account, post a message, or make a purchase, that information is sent from your web browser to a server. The server then processes this information and stores it permanently in a database. When you or another user needs to view this information later, the server retrieves it directly from the database. There are many types of databases, each suited for different kinds of data and access patterns, but their core purpose remains the same: to be the reliable long-term memory for an application. Relational databases, e.g., MySQL, PostgreSQL, SQL Server. These are like traditional spreadsheets with rows and columns, where data is organized into structured tables with predefined relationships between them. They are excellent for highly structured data where consistency and adherence to predefined rules are paramount, e.g., financial transactions, user accounts. NoSQL databases, e.g., MongoDB, Cassandra, Redis. These offer more flexible ways to store data, often without strict schemas. They are designed for scalability and handling large volumes of unstructured or semi-structured data, evolving needs, and high-performance, e.g., social media feeds, sensor data, often caching. Regardless of the type, the database is where the core, enduring state of most web applications resides. Server sessions, the attentive host. While databases handle long-term persistence, sometimes the server needs a temporary memory of a specific user's activity during their current visit. This is managed through server sessions. Think of a server session as a conversation that the server is having with a particular user. When you log into an online banking website, the server creates a unique session for you. This session remembers that you are logged in, who you are, and perhaps some temporary preferences or flags for your current interaction, e.g., this user just clicked transfer funds. How it works. When a user first interacts with a server that supports sessions, the server typically generates a unique session ID. This ID is then sent back to the user's browser, usually stored in a cookie, remember cookies from Chapter 2. For all subsequent requests within that session, the browser sends this session ID back to the server. The server then uses this ID to retrieve the specific session data it has stored for that user. Purpose. Server sessions are crucial for maintaining user authentication status, tracking user-specific preferences during a visit, or managing the state of a multi-step process like a complex application wizard that spans several pages but doesn't need to be stored in the database yet. Ephemeral nature, server-side. Similar to client-side session storage, server sessions usually have a timeout. If a user is inactive for a certain period, the session expires and the server forgets that temporary state. This is why you get logged out of inactive banking sites. APIs, the couriers of state. Application Programming Interfaces, APIs, are the crucial communication channels between the client, your browser, and the server. When your web application needs to fetch data from the server, e.g., a list of products, or send new data to be saved, e.g., a newly created user profile, it does so by making requests to specific API endpoints. Fetching state, get requests. The client asks the server for current state data, e.g., give me all the items in my shopping cart. The server retrieves this from its database or internal memory and sends it back to the client. Updating state, post, PUT, delete requests. The client sends new state data to the server, e.g., add this item to my cart, update my profile information, delete this post. The server then processes this, typically updating its database, and sends a confirmation back to the client. APIs are not state themselves, but they are the mechanisms through which client-side applications interact with and manipulate server-side state. WebSockets, real-time state sync. For applications that require real-time, bidirectional communication, like chat applications, online gaming, or live dashboards, traditional request-response APIs can be too slow. This is where WebSockets come in. How they work. Unlike standard HTTP requests, which open a connection, send a request, get a response, and close the connection, WebSockets establish a persistent, open connection between the client and the server. Real-time updates. This always-on connection allows the server to push updates to the client in real time, without the client having to constantly ask for new information. For example, in a chat application, when someone sends a message, the server immediately pushes that new message to all connected clients. Use cases: collaborative editing, live notifications, stock tickers, online auctions. WebSockets drastically optimize the flow of state data when immediate updates are critical. Why server-side state is the backbone. Server-side state forms the indispensable backbone of most complex web applications because it provides persistence. Data stored server-side survives browser closures, device changes, and time, ensuring information isn't lost. Centralization. A single, authoritative source for data ensures consistency across all users and devices. Everyone sees the same, correct version of the data. Security. Sensitive data like user credentials, financial information, or proprietary business logic is protected on the server, away from direct client access. Access to this data can be carefully controlled and audited. Scalability. Servers are built to handle simultaneous requests from thousands or millions of users, providing a robust infrastructure for data management. While client-side state focuses on making the user interface immediate and interactive, server-side state is about reliable data storage, ensuring that the critical information underpinning the entire application is safe, consistent, and always available. The interplay between these two forms of state is what defines the experience of a dynamic web application. The challenge, as we'll see, is how to effectively synchronize and manage this state when it exists in two different places, sometimes with different requirements for its lifetime and consistency. 5. The challenge of complexity. Why state management gets hard. We've explored what state is and where it lives. In primitive browser storage, in the memories of our client-side applications, and persistently on the server. For small, simple web applications, managing this state might seem straightforward. You have a few variables here, a bit of local storage there, and a database on the server. Easy, right? The reality is that as web applications grow in size, features, and the number of people working on them, state management quickly escalates from a minor concern to one of the most challenging aspects of development. When not managed strategically, state can transform from a helpful memory into a tangled mess that leads to bugs, performance issues, and developer frustration. Let's delve into why state management can become so difficult. The spaghetti code problem. Imagine a small, friendly office where everyone knows everything about everyone else's tasks. Information flows freely, and things generally get done. Now imagine that office suddenly grows into a massive corporation with hundreds of departments, each with its own internal processes, but still trying to share information by everyone just shouting across the cubicles. Chaos, right? In software, this is akin to spaghetti code, a highly unstructured and tangled codebase where the flow of logic is difficult to follow. When it comes to state, this manifests as unpredictable side effects. Changing one piece of data in one part of the application unexpectedly causes something else to break or change in a completely different, seemingly unrelated part. Difficulty in debugging. When something goes wrong, tracing where the state was last correctly updated, what action changed it, and why it changed can feel like searching for a needle in a haystack. There's no clear audit trail. Fragile code base. Adding new features or fixing bugs becomes a nightmare because any modification risks breaking existing functionality. Developers spend more time fixing regressions than building new things. Prop drilling or handing down the mail. Modern web applications are often built using a hierarchical structure, like a family tree. A main app component might have header and footer components, and the header might contain a user profile component, which in turn contains a username component. Sometimes, a piece of data, let's say, a user's theme preference is needed by a component deep down the tree, like the username component, even though many components in between, like header or user profile, don't directly use that theme preference. Prop drilling is the term for passing this data down through multiple layers of components, even through components that don't need it, just to get it to a child component that does. Why it's a problem: verbosity and clutter. Your code becomes bloated with props that aren't actually used by the components they pass through. Maintenance headache. If you change the name or type of the theme preference, you have to update every component in the chain, not just the one that produces it and the one that consumes it. Reduced readability. It becomes harder to understand which data is relevant to which component, obscuring the component's true purpose. It's like delivering a sensitive letter from the CEO to a junior intern. Instead of direct delivery, the CEO passes it to their VP, who passes it to a director, who passes it to a manager, who finally passes it to the intern. Each middle person is just a temporary mailbox, not a recipient. Siblings not speaking, the communication gap. Another common scenario involves components that exist, side by side, in the application's visual structure, but don't have a direct parent-child relationship. For instance, a filter component, which determines what products to show, and a product list component, which displays the products, don't directly interact. They might both be children of a larger shop page component. How does the filter component communicate its selections to the product list component? A naive approach might try to make them directly talk to each other, which leads to tangled, non-reusable components. The conventional solution is to lift state up. The filter selections would be managed by their closest common parent, the shop page. The filter component tells the shop page about its selections, and the shop page then passes those selections down to the product list. While lifting state up is a valid pattern, doing it extensively can also lead to prop drilling and can make parent components overly complex, especially if they have to manage the state and logic for many different children. Data inconsistency, the single source of truth problem. As an application grows, it's easy for the same piece of data to exist in multiple places. Imagine a user's name is displayed in the header, in a profile summary, and in a comment section. If the user updates their name in one place, what happens to the other two? If you're not careful, you can end up with different parts of your application displaying conflicting information. This leads to the single source of truth problem. Ideally, every piece of data in your application should have one, and only one, authoritative location where it lives. All other parts of the application should read from this single source. If there are multiple sources, they can easily get out of sync, leading to desynchronized UI. Visual elements don't reflect the true state of the data. Logical errors. The application makes decisions based on outdated or incorrect information. A related problem is race conditions, where multiple parts of the application try to update the same piece of state simultaneously, leading to unpredictable and often incorrect outcomes depending on which operation finishes last. Debugging nightmares. When a bug occurs in an application with poorly managed state, it can be incredibly difficult to diagnose. Mystery changes. You see data change, but you can't figure out who changed it or why. Complex call stacks. The sequence of functions that led to a state update is long and convoluted, jumping between many different parts of the application. Reproducibility issues. Bugs appear intermittently because they depend on a complex sequence of user actions or asynchronous events that are hard to replicate. Trying to debug these issues without a clear state management strategy is like trying to solve a crime without any evidence, witnesses, or a proper investigation team. The scale problem. The core reason state management gets hard is scale. What works fine for a simple 5-page website with limited interactivity quickly breaks down when you're building a rich, interactive application with dozens of screens, hundreds of components, and millions of users. The number of interactions, dependencies, and potential points of failure grows exponentially, not linearly. If you don't establish clear rules and patterns for how state is stored, updated, and accessed from the beginning, your application will inevitably descend into a state of unmanaged complexity. This leads to slower development, more bugs, and a frustrated development team. This is precisely why modern web development has seen the emergence of sophisticated state management patterns and dedicated libraries. These tools and approaches are designed to tame this complexity, providing structure, predictability, and a clearer path towards building scalable and maintainable applications. In the next chapter, we'll begin to explore these solutions. 6 patterns for order, unidirectional data flow, and reactivity. In the previous chapter, we explored the chaos that can ensue when state is left unmanaged in growing web applications. The symptoms: spaghetti code, prop drilling, conflicting data, and debugging nightmares, all point to a fundamental need for structure. Just as architects use blueprints to design buildings and engineers follow schematics for machines, software developers rely on design patterns to bring order to complex systems. When it comes to state management, two foundational patterns have emerged as highly effective solutions: unidirectional data flow, UDF, and the principles of reactivity. These concepts, while appearing abstract, are the blueprints for building predictable, testable, and maintainable applications. The need for structure. Think of an assembly line in a factory. Each station has a specific role, and materials move in a defined direction from one station to the next. Everyone knows their job, and you can easily trace the origins of a part or the cause of a defect. This ordered approach reduces errors, increases efficiency, and makes it easier to expand the factory or introduce new products. Without such structure, a factory would be a chaotic scene of workers grabbing parts randomly, passing them in every direction, and trying to assemble things without a master plan. That's the spaghetti code we discussed. Unidirectional data flow and reactivity provide this kind of assembly line discipline for your application's data. Unidirectional data flow, UDF. The predictable cycle. Unidirectional data flow, UDF, is a paradigm where data in an application moves in a single, predictable direction. This contrasts sharply with bidirectional two-way data flow, where data can move in multiple directions, creating complex webs of dependencies that are hard to track. The core principle of UDF is based on a simple, cyclical pattern often illustrated as a loop. Action event. Something happens in the application. This could be a user clicking a button, data arriving from a server, or a timer reaching its limit. This action describes what happened. State transformation, reducer store. The action is then sent to a central place that holds the application's state. This central place contains logic, often called reducers or store logic, that determines how the state should change in response to that specific action. It effectively computes the next state based on the current state and the action. New state. The central state is updated with the newly computed state. Critically, in many UDF implementations, the old state is not directly modified. Instead, a brand new state object is created with the necessary changes. This is known as immutability, which simplifies change detection and debugging. View update. Once the state has been updated, any parts of the user interface, the view, that depend on that state automatically re-render or update themselves to reflect the new state. Repeat. The updated view is now ready for new user interactions, which may trigger new actions, restarting the cycle. Benefits of UDF. Predictability. Because data flows in one direction, you can always trace how any piece of state got to be in its current form. This linearity makes the application's behavior far more predictable. Traceability and debugging. Debugging becomes significantly easier. If something is wrong in the UI, you can follow the action backward through the state transformation to pinpoint exactly where the error occurred. Tools can even time travel through state changes. Maintainability. Changes are more isolated. Modifying how one action changes state is less likely to break unrelated parts of the application. Testability. Because the state transformation logic is pure, it's a function that takes an old state and an action and returns a new state with no side effects. It's very easy to test in isolation. Analogy. The assembly line. Imagine a car factory's assembly line. Action. A specific task is requested, e.g., attach wheels. State transformation. This request goes to the wheel station. The station, its logic, takes the car's current state, no wheels, and the action, attach wheels, and produces a new state, car with wheels. New state, the car moves to the next part of the line, now with wheels. View update. Anyone observing the car on the line sees it now has wheels. The process continues. Every change is clear, sequential, and traceable. The pub-sub, publish-subscribe pattern, decoupled communication. While UDF describes the overall flow, the publish-subscribe, pub-sub pattern is often an underlying mechanism that enables the view update step, especially in component-based architectures. What it is, in the pub-sub pattern, there are publishers and subscribers. Publishers. These are components or parts of your system that publish or broadcast information about events or changes. They don't care who listens or what happens next. Subscribers. These are components or parts of your system that subscribe or listen for specific types of information. When information they are subscribed to is published, they receive it and react accordingly. Role in state management. The central state store acts as a publisher. Whenever its state changes, it publishes that change, e.g., user profile updated, shopping cart item added. Individual UI components, the views, act as subscribers. A component displaying the user's name subscribes to user profile updated events. A component displaying the cart total subscribes to shopping cart item added events. This pattern decouples the components. The user profile component doesn't need to know anything about the cart total component or vice versa. They both just subscribe to the central state, making them independent and reusable. Analogy, a newspaper subscription service. Publisher, the news agency. It publishes news stories, events as they happen. It doesn't need to know every single reader personally. Subscribers. Readers who subscribe to specific types of news, e.g., local news, sports. When a relevant story is published, they automatically receive it. Reactivity principles. Automatic updates. Complementing UDF, reactivity ensures that the UI automatically stays in sync with changes in state. It's the magic that makes web applications feel alive and responsive. We touched on this in Chapter 3, but here's a deeper look at the principle. At its core, reactivity means that when a piece of data, state, changes, anything that observes or depends on that data automatically gets notified and updates itself. How it works conceptually. Observation. The web framework or library sets up a system where UI components observe specific pieces of state. Automatic updates. When that observed state changes, the framework intelligently determines which parts of the UI need to be re-rendered or modified, and then performs those updates efficiently. This differs from manually telling every component to update whenever data changes. Efficient updates. Modern reactive systems don't necessarily re-render the entire user interface. Instead, they often use clever techniques, like comparing a virtual representation of the UI before and after a state change, to identify and update only the necessary parts of the actual browser display, ensuring high performance. Analogy, a spreadsheet. Think of a spreadsheet where cells contain formulas. If cell A1 contains a number, and cell B1 contains the formula equals A12, then the value in B1 is reactive to A1. If you change the number in A1, B1 automatically updates without you manually recalculating it. Bringing it together. Unidirectional data flow provides the disciplined, predictable path for state changes. The publish-subscribe pattern helps decouple the parts of your application that generate state changes from those that consume them. And reactivity ensures that your user interface automatically and efficiently reflects the latest state. Together, these patterns form the conceptual bedrock upon which many modern state management solutions are built. They provide the necessary answers to the complexity challenges we discussed, turning potential chaos into a well-ordered system. In the next chapter, we will explore how popular web development frameworks and libraries implement these patterns to help developers build robust and scalable applications. 7. Framework-specific solutions. Tools of the modern web. The general principles of unidirectional data flow and reactivity, discussed in the previous chapter, are powerful concepts. However, implementing them from scratch for every web application would be an enormous task. This is where modern web development frameworks and libraries come in. Each major player in the web ecosystem provides its own set of tools, conventions, and philosophies for managing state, often built upon these core patterns. It's important to remember that while the names and specific implementations differ, the underlying problems and the fundamental solutions often share common ground. Our goal here is not to delve into intricate code examples, but to understand the conceptual approaches these tools adopt. The ecosystem of tools, the rapid evolution of web development, has led to a diverse landscape of frameworks as developers sought better ways to build complex user interfaces. React, Vue, and Angular are currently the most prominent, each offering a distinct but effective approach to organizing your application's state. React, props, context, and external libraries. React, known for its component-based architecture, provides several mechanisms for managing state. Component state, built-in use state/use reducer. Every React component can manage its own internal, local state using hooks like useState or useReducer. This is perfect for UI-specific concerns that only that component needs to know about, e.g., whether a dropdown is open, the current value of an input field. This aligns with the idea of keeping state localized whenever possible. Prop passing. This is the primary way data flows from a parent component down to its child components. If a parent component has a piece of state that its child needs, the parent passes that state down as a prop, short for property. Similarly, if a child needs to inform its parent about something, e.g., a button click, it invokes a function passed down as a prop. This mechanism strongly embodies unidirectional data flow, as data moves explicitly from parent to child. Context API. As discussed, prop drilling can become cumbersome when data needs to be passed through many layers of components that don't directly use it. React's Context API offers a solution for globalish state. It allows you to create a context that can hold data, and any component within that context's provider can access the data without explicitly passing props down through every intermediate component. Purpose, ideal for data that is considered global for a subsection of your application, like a user's authentication status, theme preferences, or language settings. Limitations. While useful, Context API alone isn't always sufficient for managing highly complex, frequently changing global application state, as updates can cause widespread re-renders if not optimized. External libraries, e.g., Redux, MobX. For very large and complex applications, where managing global state with just context becomes unwieldy, the React community has developed powerful external state management libraries. Redux. This library very strictly enforces unidirectional data flow. All application state is held in a single, central store. State can only be changed by dispatching actions, describing what happened, and these actions are processed by reducers, pure functions that take the current state and an action and return a new state. This strictness makes state changes highly predictable and debuggable, facilitating time travel debugging. Redux is opinionated but provides a clear mental model for state management. MobX takes a different, more implicit approach to reactivity. Instead of requiring actions and reducers for every change, MobX allows you to define observable state. Any component that observes this state will automatically re-render when the state changes. It offers more flexibility and often less boilerplate code than Redux, appealing to developers who prefer a more object-oriented and less restrictive style. Vue.js, built-in reactivity, and Vuex. Vue.js is known for its approachability and built-in reactivity system, which makes state management intuitive from the start. Built-in reactivity. Vue's core strength is its automatic reactivity. When you declare data in a Vue component, Vue automatically makes it reactive. If that data changes, any part of the component's template or computed properties that use that data will automatically update. This inherent reactivity simplifies many common state management tasks. Component state, data option, or ref reactive in composition API. Similar to React, Vue components can manage their own local state. You define this data within the component's options, or using ref and reactive in the newer composition API, and Vue's reactivity system ensures the UI stays in sync. Props and events. Data flows down from parent to child via props. When a child component needs to communicate something back up to its parent, it emits an event. This also adheres to a unidirectional data flow model for component communication. Vuex, Vue's official state management library. Vuex is explicitly inspired by pattern ideas like Flux, which inspired Redux, and very clearly implements a central store following unidirectional data flow principles. State, the single source of truth for your application's global data. Mutations, the only way to change the state. Mutations are synchronous functions that ensure state changes are predictable and traceable. Actions can contain asynchronous operations and commit mutations. This separates asynchronous logic from direct state modification. Getters allow you to derive computed state from the store's state, similar to computed properties for local component state. Vuex provides a highly structured and opinionated way to manage global state, making it very suitable for larger Vue applications. Angular, services, RxJS, and NGRX. Angular, being a full-fledged framework, provides powerful mechanisms for state management, often leveraging object-oriented principles and reactive programming heavily. Services. In Angular, services are singletons that can be injected into any component, service, or other part of the application. They are designed to hold and manage data, communicate with APIs, and encapsulate business logic. A service can hold application state, and components can subscribe to changes in that state. This allows for state to be shared across many components without prop drilling, as the components all access the same instance of the service. Example: a user service might hold the currently logged-in user's data, and multiple components, navbar, profile page, can inject and subscribe to this service to display or update that user data. RxJS and observables. Angular makes extensive use of the RxJS library, which brings the power of reactive programming to JavaScript. Data, events, and asynchronous operations are often treated as observables. Components can subscribe to observables provided by services and react to the data they emit over time. This is a very powerful way to manage state that changes asynchronously or flows over time, providing a robust solution for managing complex data streams. NGRX. Similar to Redux for React and Vuex for Vue, NGRX is a popular state management library for Angular that implements the Redux pattern. It establishes a single store for the application's state, modified only through actions and reducers. NGRX leverages RxJS observables heavily for managing the flow of actions, state, and effects, side operations like API calls. While powerful for large, complex applications requiring strict state predictability, it can introduce a significant learning curve and boilerplate for smaller projects. Beyond the big three, the web development landscape continues to evolve, and new patterns and libraries emerge constantly. Frameworks like Svelte, for instance, offer even more direct and simpler approaches to reactivity, often compiling components to highly optimized JavaScript that inherently manages state efficiently. Libraries exist for more atomic state management, like Zustand or Jotai for React, focusing on small, independent pieces of state reactive across components. Even without explicit state management libraries, modern web tools such as React Query or Apollo Client for GraphQL significantly simplify the management of server-side data on the client. No one-size-fits-all. The choice of state management solution, whether built-in or external, depends heavily on application size and complexity. A small marketing site might be perfectly fine with local component state and props. A large e-commerce platform will almost certainly need a global store. Team familiarity and preference. Developer comfort with a particular paradigm plays a significant role. Performance requirements. Some solutions offer more fine-grained control over rendering and performance optimizations. Specific features. Real-time demands might push towards solutions leveraging WebSockets and reactive streams. While the tools and idioms change, the core problems they solve, predictability, manageability, and scalability of application memory, remain constant. Understanding the underlying principles of unidirectional data flow and reactivity will equip you to navigate any new framework or library that comes your way. Having explored these specific solutions, our next step is to hone in on a critical decision. When does data belong in a component, and when does it need to be shared globally? 8. Global vs local. Deciding where your data lives. By now, we understand that web applications have memory, called state, and that managing it effectively is crucial. We've seen how web browsers offer primitive ways to store state, Chapter 2, how client-side applications manage their in-memory state, Chapter 3, and how critical server-side state is for persistence, Chapter 4. We also touched upon the complexities that arise from unmanaged state, Chapter 5, and the patterns and tools, Chapters 6 and 7, designed to bring order. Now, a fundamental and recurring question for any web developer is, should this piece of data be stored locally within a single component, or should it be part of a broader, global application state accessible to many components? Making the right decision here is paramount for building applications that are not only functional, but also maintainable, scalable, and easy to understand. Misplacing state can lead to the very problems we discussed: prop drilling, data inconsistency, and debugging headaches. The fundamental question, who cares about this data? The simplest way to start answering the global versus local question is to ask, does this data affect only the component that defines it, or does it need to be accessed or changed by other, unrelated components? When to use local component state. Local state is the private thoughts of a component. It's information that is exclusively owned and managed by that component, and no other component explicitly depends on its value. Using local state is generally the simplest and most performant option when appropriate. Use local state when UI-specific concerns. The data relates solely to the behavior or appearance of a single component. Examples: is a drop-down menu open or closed? What is the current value of a user typing into an individual input field before submission? Is an image carousel showing the first, second, or third image? Is a modal dialog box visible or hidden? Ephemeral data. The data is temporary and doesn't need to persist beyond the component's current lifecycle or beyond the immediate user interaction. If the component is removed from the screen, this state can safely disappear. Encapsulation. It isolates changes. If a bug occurs due to this local state, you know exactly where to look within that component. Performance. Modifying local state typically triggers fewer re-renders or updates compared to global state, as only the component and its immediate children, if they depend on it, are affected. Example: a save button. A save button might have local state like is saving, Boolean, and message, string. When clicked, is saving becomes true, disabling the button, and message becomes saving. When the save operation completes, is saving becomes false, and message becomes saved, or error saving. This state is entirely local to the button and its immediate display. When to use global application state. Global state, or application-wide state, is the shared knowledge of an application. It's data that needs to be accessible to many different components, often in different parts of the application's UI hierarchy, or data that needs to persist across different views or routes. Use global state when shared data. The data is relevant to multiple, often disparate components. Examples: the authenticated user's ID and profile information, global application settings like theme preference, language, items in a shopping cart, which might be displayed in a cart icon in the header, a full cart page, and in a checkout summary. Cross-cutting concerns. The data influences aspects of the application that span across many features or screens. Persistence across views. The data needs to remain consistent as the user navigates between different pages or routes within a single-page application. E.g., your shopping cart items should remain when you move from product page to checkout. Complex interactions. When a change in one component needs to trigger updates in many other, potentially unrelated components. Example: user authentication status. Whether a user is logged in or not affects almost every part of a complex application. The navigation bar showing login versus logout and profile info. Access to protected pages, displaying user-specific content, etc. This is clearly global state. The lift state up principle. What happens if a piece of state starts out local to a component, but then a sibling or an unrelated component suddenly needs access to it? The answer is to lift state up. This principle involves moving the state to the nearest common ancestor component that shares an interest in that state. Once the state is in the parent can then pass it down as props to any of its children that need it. Example: imagine you have two separate components: temperature input for Fahrenheit and temperature display for Celsius. Initially, temperature input might keep its input value as local state. But if temperature display needs to show the Celsius equivalent, and it needs the Fahrenheit value to do so, you lift the Fahrenheit value up to their common parent, e.g., a temperature converter component. The temperature converter component then manages the Fahrenheit value state, passes it down to temperature input as a prop. which temperature input updates via a callback prop, and also passes it to temperature display as a prop, allowing temperature display to perform the conversion. While lifting state up solves the immediate problem of shared state between siblings. If the state has to be lifted very high up the component tree, it can lead to the prop drilling problem we discussed in Chapter 5. This is often an indicator that you might need a more global state management solution, like a dedicated store, for that piece of data. Pitfalls of misplaced state. Over-globalizing state. If you put everything into global state, even data that is only relevant to a single component, you can add unnecessary complexity. Your global store becomes bloated. Initial rendering might be slower, and every little change might trigger larger parts of the application to re-render, even if they don't depend on the specific data that changed. It's like having a central committee decide every tiny detail, even if a team member could decide it on their own. Under-globalizing state. Trying to keep everything local when it really needs to be shared leads to excessive prop drilling. Your components become verbose, and the component tree becomes hard to traverse and reason about. Communication problems. Components struggle to interact, leading to convoluted workarounds, event buses, or direct manipulation of other components, which is almost always a bad idea. It's like expecting everyone in a large organization to individually keep track of vacation days for all colleagues, rather than having a central HR system. A practical decision-making checklist. When uncertain about where to place state, consider these questions. Directly affected scope. Is this data only and exclusively used by this single component, and perhaps its immediate, non-reusable subcomponents? If yes, local state is a good fit. Shared across components. Do multiple, unrelated components need to access or modify this data? If yes, consider global state or lifting state up to a common parent. Persistence across navigation. Does this data need to persist when the user navigates to a completely different page or route within the application? If yes, it's likely global state or server-side persistence. Frequency of change. How often does this data change? Very frequently changing data might benefit from optimized local or context-specific state, while static or rarely changing data is fine in global stores. Data source. Is this data coming directly from a server API that many components consume? This often points to global state managed by a data fetching library or a dedicated store. There's no one-size-fits-all answer, and effective state management is often about balancing these considerations. By consciously deciding whether state belongs globally or locally, you lay the groundwork for a more organized, efficient, and enjoyable development process. In the final chapters, we will explore advanced topics and best practices, including how to ensure all this well-managed state performs optimally, is thoroughly tested, and can be easily debugged. 9. Advanced topics and best practices, performance, testing, and debugging. We've now covered the what, why, and how of state management, from fundamental concepts to specific tools and the crucial global vs local decision. However, building a functional application is only part of the journey. For an application to be truly successful and sustainable, its state management must also be performant, reliable, and debuggable. This chapter delves into advanced considerations and best practices that elevate state management from merely working to working well. Performance considerations. Poorly managed state can lead to sluggish applications, frustrated users, and missed business opportunities. Optimizing state performance is primarily about two things: avoiding unnecessary work and making the necessary work as efficient as possible. Minimizing re-renders/updates. The problem. In reactive systems, like React, Vue, Angular, when state changes, components that depend on that state re-render or update. If components re-render too frequently or re-render large parts of the UI when only a tiny piece of state has changed, it can lead to noticeable slowdowns. Best practice. Understand how your chosen framework or library detects changes and triggers updates. Use features like React Memo, Use Callback, Use Memo in React, or fine-grained reactivity in Vue and Svelte to prevent unnecessary re-renders of child components that haven't received new props or whose state dependencies haven't truly changed. Avoid putting very volatile, frequently changing state high up in the component tree if it causes wide-ranging, inefficient updates. Memoization and caching. What it is. Memoization is an optimization technique where the result of an expensive function call is stored, cached, so that if the same inputs occur again, the cached result is returned instead of re-executing the function. Application to state. This is especially useful for derived state. Calculations that combine or filter existing state, e.g., calculating a total price from a list of shopping cart items, filtering a large list of products. If the underlying items haven't changed, the total doesn't need to be recalculated. API responses. Caching data fetched from a server means you don't have to refetch it on every navigation or component mount. Libraries like React Query or SWR excel at managing this network state caching layer. Benefit: reduces CPU cycles, leading to smoother UI interactions and faster data display. Debouncing and throttling. The problem: user interactions can be very rapid, e.g., typing quickly into a search box, resizing a window, rapid scrolling. If every single event immediately triggers a state update or an expensive operation, like an API call, the application can become overloaded. Debouncing ensures a function is only called after a certain amount of time has passed since the last invocation. Think, only search after the user stops typing for 300 ms. Throttling ensures a function is called at most once within a specified period. Think, only process scroll events every 200 ms. Benefit: reduces the number of times state is updated or expensive operations are performed, improving responsiveness. Testing state. A well-managed state system is inherently more testable. Comprehensive testing ensures that your application's memory behaves exactly as expected, reducing bugs and building confidence during development and deployment. Why test state logic? State mutations are often the core business logic of an application. Testing them ensures correctness. Testing provides living documentation of how your state responds to various actions. Unit testing state logic. Focus: test the smallest, isolatable parts of your state management. Example: if you use Redux, you would write unit tests for your reducers to ensure they correctly transform old state into new state when given specific actions. These tests are typically pure function tests, no UI involved. Benefit: fast, reliable, and helps pinpoint bugs precisely. Integration testing. Focus: test how different parts of your application that interact with state work together. This might involve components interacting with a state management store or services interacting with an API and updating state. Benefit: verifies the interaction points and data flow between different modules. End-to-end E2E testing. Focus: simulate a full user journey through your application from the user's perspective. For state management, this means verifying that a user action, e.g., adding an item to a cart, correctly updates global state, persists data if applicable, and is correctly reflected across multiple pages or UI elements. Benefit: provides the highest confidence that the entire application, including its state, functions correctly in a real-world scenario. Debugging state. Even with the best planning and testing, bugs happen. When they do, clear state management makes debugging significantly less painful. Browser Developer Tools, Element Inspector, helps you see the current rendered HTML, which implicitly reflects UI state. Console, essential for logging state values at various points. Network tab, crucial for understanding how data is flowing between your client and server, spotting API call issues. Application tab. This tab is where you can inspect local storage, session storage, and cookies directly. DevTools extensions. Many popular state management libraries and frameworks offer specialized browser extensions, e.g., Redux DevTools, Vue.js DevTools, React DevTools. Features: these are invaluable. They allow you to inspect current state, view the entire application state tree at any given moment, track state changes, see a historical log of every action or event that mutated the state. Time travel debugging. Revert the application's state to a previous point in time, then step through the actions one by one to see exactly how the state evolved. making it incredibly easy to find the exact moment an error was introduced. Action playback, redispatch actions to observe their effect. Strategic logging, while dev tools are powerful, sometimes simple console log, statements, or more sophisticated logging libraries are your best friend. Best practice. Log state values at key moments, especially before and after a state transition or when a component receives new props. Be mindful not to leave excessive logging in production code. The state snapshot mindset. When debugging, always think, what should the state look like right now, given these inputs and actions? Compare your expectation with the actual state observed in dev tools. This helps pinpoint discrepancies quickly. Security for state. While not a typical performance or debugging concern, security is paramount when storing any data. Never store sensitive data client-side, unencrypted. User passwords, API keys, or highly sensitive personal information should never be stored directly in local storage, session storage, or cookies without strong, server-provided encryption. If an attacker gains access to a user's browser, this data could be compromised. Sensitive data should primarily reside on the server and be accessed securely via authenticated APIs. Sanitize inputs. Always ensure any data coming from user input or external sources is properly sanitized before it's used to update state or rendered in the UI, to prevent cross-site scripting, XSS, attacks. By diligently applying these performance optimization, testing, and debugging strategies, you move beyond merely implementing state management to mastering it. A well-constructed state layer is the foundation of a robust, efficient, and enjoyable web application for both the users and the developers. In our final chapter, we'll cast our gaze towards the horizon, discussing emerging trends and the enduring principles that will continue to guide the evolution of state management. 10. The future of state. Emerging trends and next steps. We've journeyed through the intricate world of state management, from the fundamental concept of an application's memory to the complex patterns and tools that engineers employ to keep that memory organized, consistent, and performant. We've seen that state is the undeniable heart of any interactive web application. However, the web development landscape is an ever-evolving frontier. New tools, paradigms, and best practices emerge constantly. While it's impossible to predict precisely what the future holds, we can observe current trends and understand how they might shape the way we manage state in the years to come. More importantly, we can reflect on the enduring wisdom that transcends technological fads. Emerging trends in state management. The blurring lines between client and server state. Historically, client-side state and server-side state were distinct. Client-side state was what stayed in the browser, and server-side state was what lived in the database. Server components, server-side rendering, SSR, enhancements. Frameworks like Next.js, with React server components, and Astro are pushing the boundaries. They allow rendering parts of the UI on the server, potentially fetching data directly from databases there, and then sending optimized HTML to the client. This means some client-side concerns are being pushed back to the server, simplifying client-side data fetching and reducing the need for extensive client-side JavaScript. This changes where state is managed and who, client or server, is responsible for it. Edge computing. As applications move closer to the user, at the edge of the network, state might be managed in distributed ways, leading to new challenges and solutions for data consistency and synchronization. Atomic state management. While large, centralized global stores like Redux or Vuex solved many problems, for some applications, they can feel overly verbose or rigid. Recoil Jotai, Zustand for React, Pinia for Vue. These libraries represent a shift towards more atomic or modular state management. Instead of one monolithic global store, state is broken down into smaller, independent, shareable units. Components subscribe only to the specific atoms of state they need, leading to more targeted updates and often less boilerplate. This approach still leverages reactivity and often unidirectional flow, but with a more granular focus. Data fetching libraries and server state synchronization. Libraries like React Query, SWR, and Apollo Client for GraphQL are becoming increasingly popular. They simplify the process of fetching data from a server and automatically manage the caching, synchronization, background refetching, and error handling of that server-side state on the client. They effectively act as a dedicated layer for managing asynchronous data, often alleviating the need to store this data within a general-purpose global state management solution. This allows the global state solution to focus primarily on application-specific UI state rather than remote data. WebAssembly, WASM, and beyond. WebAssembly allows code written in languages like C++, Rust, or Go to run in web browsers at near-native speeds. As WASM capabilities expand, it could open up new possibilities for how complex state logic, simulations, or even entire application backends operate directly within the browser, leading to novel state management paradigms. The importance of fundamentals. Despite the constant innovation, a crucial truth remains. While the tools change, the core problems and their underlying principles often do not. State is memory. This fundamental definition remains constant. Every interactive application, regardless of its technology, needs to remember things. Complexity demands structure. As applications grow, the need for organized data flow, clear responsibilities, and predictable behavior will always be paramount. The spaghetti code problem is timeless. Unidirectional data flow is powerful. The elegance and predictability of data flowing in one direction, transitioning state reliably, is a pattern that has proven its worth across many technologies and will likely continue to do so. Reactivity is key to responsiveness. Users demand immediate feedback. Systems that automatically update the UI when data changes will always be preferred. The global versus local dilemma persists. Deciding where a piece of data should live, whether it's truly shared or isolated, is a decision you will make repeatedly, regardless of the framework. Your next steps. The journey into state management doesn't end with this book. It's a continuous process of learning and adaptation. Practice the principles. Don't just understand the tools, understand why they exist and the principles they embody. Learn to identify situations that call for specific state management strategies. Experiment with new tools. Keep an eye on new libraries and frameworks. Try building small projects with different approaches to understand their strengths and weaknesses firsthand. Read the documentation. High-quality documentation is invaluable. Developers put immense effort into explaining their tools' philosophical underpinnings and practical usage. Engage with the community. Forums, online courses, and local meetups are great places to learn from others, share experiences, and stay updated. Build. The best way to solidify your understanding is to apply what you've learned. Build projects, big or small, and intentionally wrestle with state management challenges. Concluding thoughts. Managing the unseen. A clear guide to state in web applications has aimed to demystify complex concepts, providing you with a solid foundation. You now understand that state is not some abstract, intimidating concept, but the very memory that breathes life into web applications. You're equipped to recognize the challenges of managing this memory and appreciate the elegance of the solutions developed to overcome them. The web will continue to evolve, but with a deep grasp of state management fundamentals, you are well prepared to adapt, innovate, and confidently build the next generation of dynamic, performant, and user-friendly web applications. Go forth and manage that unseen, vital heart of the web.